blood order to be done to do for exchange. There's like, say, 5 short answers, you think? Maybe more than that?
Okay, we'll make a start and then I'll pull it up in a minute. Okay, so, oh. Like when they change software, isn't it supposed to get easier to use, not harder to use? Isn't that the whole point? I don't get it. Okay, so we looked at the change in the heart when we do weight training or aerobic. We looked at blood pressure changes for aerobic and weight training. All right. So now we're going to look at the vascular system as opposed to the heart. So what's going on? We know what's going on here. What's going on around the rest of the vascular system when we're exercising, right? So our main transporter, one of the things we're most interested in is the red blood cell, because that's our bus system for our oxygen. Right? Without oxygen, all our ATP production, if we're trying to move for any length of time, starts going downhill quickly. So the goal is how much oxygen can we get to the muscles in order to produce ATP. So our red blood cell is the transporter, and it can pick up oxygen because of its structure, and it has an iron in it, which when we come back later on to look at nutrition and special populations, iron and the lack of iron, having anemia, dramatically increase aerobic performance because it impacts how well hemoglobin can do its job picking up oxygen and getting it down to the muscle tissue. Right? So more hemoglobin, i.e. more red blood cells, would mean that we were better at transporting oxygen. So in adults, red blood cells are made in your marrow, in your long bones. So arms, fingers, toes, legs, right? And just before they're released from the marrow into the bloodstream, the nucleus is dissolved, breaks up. So red blood cells, unlike other cells in the body, can't regenerate or fix themselves. So they have a very short lifespan, only about 4 months. Okay? And that means that we have to replace those very rapidly on a regular basis. Typically, particularly at your age, what we see is that red blood cell production in the marrows balances out red blood cell death in the bloodstream. All right, so in a healthy person, I would expect red blood cell level in the bloodstream to stay relatively constant because I'm making them at the same speed that I'm breaking them down. Ooh, wrong. Go away. This is what happens when you don't get time for lunch. All right. So we expect them to be balanced over time in a healthy person. If you look at figure 6.12, they're looking at levels of hematocrit. So hematocrit is the ratio of red blood cells to the plasma, right? And when I look at an athlete, particularly with aerobic training increases red blood cell count. That makes sense, right? We said that adaptation is normally positive. So the body is going to adapt to do something that helps me be better at the task I'm setting it. So more oxygen would be useful for an aerobic athlete. And so what we see is higher levels of red blood cells in a trained aerobic athlete. They also increase their blood plasma volume. So overall, an endurance athlete has higher blood volume with more red blood cells, more ability to carry oxygen, which means that their oxygen delivery is greatly increased over either a typical person or someone that's doing more weight training than aerobic training, right? So red blood cell count goes up if I do aerobic training. We don't see any change in red blood cell count if we're doing weight training. If I look at plasma volume, then we have two different things going on. So it depends whether I look at what immediately happens if I go and train right now versus what do we see happen over time if I consistently train on a regular basis, right? So the immediate effect, the acute effect on plasma volume, doesn't matter which type of training we're doing, is that we see a pretty immediate drop in plasma volume at the beginning of the exercise session. Okay? In the short term, moving plasma out of the bloodstream increases the ratio of red blood cells to plasma. So that means in the short term then, we kind of fake increase oxygen capacity, oxygen carrying capacity for the bloodstream, right? So we see it with both types. It's obviously more beneficial if I'm doing an aerobic bout, but if you're going to be doing some circuit type work, you're also going to get a big benefit from that drop in plasma volume. If your aerobic exercise is quite a long training session, then over time during the training session, you're going to see a decrease in plasma volume of anywhere up to 10 to 20%. Okay? Particularly if it's hot and humid, because you're going to be sweating and that decreases plasma volume as well. So there's lots of impact. Means that if you don't stay hydrated, over time this decrease in plasma volume is going to impact aerobic performance because your blood is going to get thicker, doesn't put you really at much risk health-wise, but it can impact performance. With weight training, you don't see quite such a large, you might go as high as 20%, but with weight training, because typically we're doing something and then having a rest and then doing something, you generally don't see quite such large decreases. We also don't tend to train in the weight room for as long as we might do an aerobic bout, right? Particularly with the new kinds of training programs that are coming out. They're trying to get you in and out of the gym as quickly as possible with the biggest strength gain. Okay? So I'm not likely to be in the weight room for 2 hours. Quite a lot of people go out and run or bike for 2 hours. Over time then, so this is the chronic picture. If I look at the acute picture on it. So if I look at the acute picture, I see changes in plasma volume for both aerobic and weight training. If I look at the chronic picture, then what I see is a long-term effect of plasma volume increase in an aerobic athlete, anywhere up to 20% when we're looking at plasma volume at rest. Okay. So, because we said on Wednesday that aerobic training changes end diastolic volume, changes stroke volume, changes Q. Right? So over time then, plasma volume goes up with aerobic training. That means I can get higher levels of EDV at the end of relaxation, which increases stroke volume, which increases Q. More blood out per minute means more oxygen delivery, more nutrition delivery. Okay, so again, the adaptation is always positive. Okay. So, increase in plasma volume also helps with some temperature regulation if you're exercising in a hot environment. So there's quite a few benefits to that plasma volume adaptation with aerobic training. Weight training, there's not really research to support that we see the same increase over time. Right? So we don't see the adaptation with weight training. Makes sense, weight training doesn't use oxygen, mostly. Right? It's typically considered an anaerobic training. Now, with the kinds of programs that Coach LV is initiating, I suspect that when the research catches up with those programs, we'll see some different outcomes, because the kind of work he has you doing is quite a bit more aerobic than a typical strength program. So my suspicion is that when we see research on those kinds of programs, that we'll see some change in plasma volume with those programs as well. But right now, the research is on a traditional kind of weight program, and we don't see a change with that programming. This is the, okay, so you're looking at chapter 6, not chapter 5 anymore, okay, but the table is the same table in the new version of the book. Okay. So this table is great because it summarizes everything that's going on for you. When we look at rest, right, what are the adaptations that we see at rest in the cardiovascular system due to either aerobic or strength resistance work? So in particular, I think it's interesting, right, here's our diastolic blood pressure. Okay? So we see decreases in resting diastolic blood pressure, that's the lower number, the relaxation number, with aerobic and strength training. Likely to see more decrease with aerobic training, but you do see some change with strength training. Right? Just remember, you wouldn't put someone in a heavy strength resistance program if they've got high blood pressure. Okay? Get it down first because of the changes in blood pressure that we see with weight training. Systolic blood pressure goes down at rest if I exercise regularly. Stroke volume, right? How much blood comes out per beat increases if I do aerobic work, doesn't change very much if I do resistance work. Again, makes sense, because if I'm doing aerobic work, I need more oxygen, and so we see changes in how much oxygen delivery there can be. What else on here? Let's see. We see decreases in heart rate, resting heart rate. Remember, if we're doing aerobic work, not if we're doing resistance work. Oh, no. Can't go there yet. So that's at rest. If I'm in my exercise, if I'm doing my training program, then over time, cardiac output will increase for the same amount of work. Right? That means that I don't have to work as hard because I've got more blood flow. Cardiac output going up means I get more oxygen delivery to skeletal muscle, so I'm able to produce more ATP. So all the adaptations lead to increase in performance. Right? So if I train aerobically on a regular basis, I will have more blood flow per beat, which means I have more oxygen delivery per beat to skeletal muscle, which means I'm able to make more ATP. And so my aerobic performance will go up. I can either run faster or I can run for longer. If I'm weight training, then when I'm exercising, we see an improved ability to maintain Q. Okay, so what I mean by that is, remember that we said that the pressure was the highest. Which way around is this valve? I think it's that way around. Pressure was the highest in the aorta, in the whole system. And when we do weight training, the pressure's even higher. Okay? So I've got to contract the heart hard enough to push the valve open against all this pressure the other side. Okay? So the more weight training I do, the better able I am at getting the blood out. Leads to cardiac output, right? Q. How much blood can I get out per minute is Q. If I'm having to work against harder pressure, then if there was no adaptation in the heart, you would expect Q to go down while you were doing the lift. That's not what we see over time. So over time, the heart gets strong enough that it can maintain Q even though the pressure this side of the valve is so high.
And how come with resistance work, you're not increasing your stroke volume? Because if you're able to push more...
That's at rest.
Oh.
This is at rest.
Well, yeah, but still, so I would think that you're strengthening it, so...
Yes,
at rest it should still increase.
Right, but remember at rest, we don't see any change in Q. Whether I'm a trained person or an untrained person, because Q is all about oxygen delivery at the level that's necessary for the work you're doing. Is that? So when I'm resting, even if I've trained, my Q doesn't need to be any higher than it is when I wasn't a trainer. Okay. All right. So, what's happening to help with the changes other than increased left ventricular mass, left ventricular wall thickness, oxygen delivery to the tissues? The first thing we want to look at. The goal is to get more oxygen into the muscle. And we have this nice ugly term, arterial venous oxygen difference. Again, if the big words are a nuisance, AVO2 difference is the short version. And what we're looking at is how much oxygen is in the bloodstream as the arteries enter and then turn into arterioles, and then we're looking at the capillary network around the muscle tissue. How much oxygen is there in the venous return when you come out of the muscle, the other side, how much oxygen is in the capillary network, in the venules, and then in the veins, coming back to the heart. Because that tells us how much oxygen was actually delivered to the muscle tissue, and that's the key. How much oxygen do we actually get? Doesn't matter how much I pick up at the heart or the lungs, if when I get down to the muscles, it's not getting out of the bloodstream and into the muscle tissue. Right? Because I don't make ATP in my bloodstream. I make ATP in the muscle. So all this oxygen that I'm managing to carry on hemoglobin is great, but I have to be able to get it off into the blood, into the muscle tissue when we get to the skeletal muscle. So at rest, AVO2 difference is somewhere around 5 milliliters per 100 mils. Okay, so here's rest. Here's the bloodstream coming in. The capillary, remember the capillary is the level where the blood is the closest to the muscle tissue. That tiny, tiny, tiny membrane gap that we were talking about. Right? So the capillary network is wrapped around the muscle tissue. So when I come in, at rest, on average, somewhere around 20 milliliters of oxygen per 100 mils. When I look at the blood, the other side of the capillary network, 15 or so milliliters of oxygen per 100 mils. So, 20 minus 15 means I dumped off 5 milliliters worth of oxygen. Because at rest, I don't need to make a lot of ATP. Yes, you're working aerobically when you're sitting here, but the level of work is so low that you don't need a lot of oxygen to be able to create the amount of ATP you need. During exercise, right, so if we look at very heavy aerobic work, then what we see is same amount of blood in the artery coming in, because I don't suddenly develop at that, right? From rest to exercising, I don't suddenly grow red blood cells. That takes time. So I've still got my 20, but when we check the other side, somewhere around 5, depending on how much work I'm doing and who I am and what kind of muscle tissue I have. Okay? So in this example, we have 5 milliliters the other side. So 20 minus 5, I dumped off 15 milliliters of oxygen instead of 5. Okay? So if we go all the way back to that lab that we did where we were passing the tennis balls down, okay? For our electron transport chain to make heaps and heaps and heaps of ATP, I have to have available oxygen at the other end to pick up the hydrogen. So here's my increase in oxygen availability to pick up hydrogen to make more ATP. Yeah. There's lots of glassy eyes. I know it's Friday afternoon, guys, but hang in. Does that make sense, right? I have to be able to get, if we go back to our tennis balls, I've got to have a mechanism of getting more oxygen into the muscle cell so that I can make more ATP. Right? So AVO2 difference is the measure of that increase in oxygen transfer into the muscle tissue. All right, so Fick equation then is the name of how we measure oxygen delivery. Fick was the chap that came up with this equation. Oxygen delivery, based on everything we've said this week, is how much blood can I get down to the muscle, because the blood has the oxygen in it, multiplied then by this AVO2 difference. How much oxygen can I get out of the bloodstream? Okay. So how much can I get there? How much can I get there? Multiplied by how much can I get out? Oxygen delivery drives VO2 max. Guys, if it's that funny, go away, okay? I'm working really hard here. Oxygen delivery drives VO2 max, right? We said VO2 max is my capability of utilizing oxygen to make ATP. Right? Best measure of intensity, not very realistic for us on the playground or out on the track or out on the football field, but VO2 is how much oxygen am I using at the tissue level, not how much oxygen am I breathing in, how much am I using. To use it, I have to get it in, and I have to get it down there, and I have to get it out of the bloodstream and into the muscle. So, blood flow, Q. How much blood comes out of the heart per minute? Multiplied by a VO2 difference, how much blood is leaving the blood, how much oxygen is leaving the bloodstream and going into the tissue. Q is heart rate times stroke volume. So here's our Fick principle. Okay. You can use that principle for a segment. Okay. How much oxygen are the muscles in my forearm using to play a game of tennis? Or you can use it for the total system. How much oxygen is my whole body using to play this game of tennis? Right? It can be used at either level. So when you're reading about it, just be aware of the fact that, make sure you know what are they talking about one limb, one muscle group, or are they talking about the entire body? If that's oxygen delivery, then if I want to change oxygen delivery, I've got two choices, right? I can change Q, or I can change how much oxygen I'm taking out. Okay. Or I can combine those and get massive more amount of oxygen into the muscle tissue. If I want to increase blood flow, then I need to be able to redistribute blood flow, because I can't suddenly grow more blood because I decide to go on a 10-hour hike. Okay. So if I want to increase blood flow, I don't grow more blood, I have to move blood from somewhere else. Okay. So redistribution is a crucial factor when we're looking at oxygen delivery to a particular tissue. So I have this diagram in the PowerPoint notes. If you look in the textbook, they have a pie chart version, but they're saying the same thing. All right, so they've got this pie chart. Here's my pie chart at rest. Where is the blood going? Here's my pie chart when I'm exercising. Where do I redistribute the blood to? So when we look at, so on this one, the top, this is exercise, and here's my percentage blood flow, and here's rest and my percentage blood flow. All right, so 5 liters per minute, Q, 5 liters per minute at rest. This uses a 25 liter, that's a lot. Okay. So I'm going to move it to where I need it. So when I look at the muscle at rest, somewhere around 15 to 20% of your cardiac output goes to your skeletal muscles. So while you're sitting here, not quite a quarter of your blood flow is going to your muscles to provide nutrients and oxygen to your muscles for sitting still. If I look at heavy exercise though, 70 to 85% of Q is going to my muscles because I need all that oxygen and all that nutrition at the muscle tissue so that I can work that hard. If you look at your stomach, 20 to 25% of cardiac output at rest goes to your digestive system. If we look at heavy exercise, only 3 to 5% of cardiac output goes to your digestive system. So that's another reason why you should not eat a large meal or anything that is not going to digest very quickly just before you exercise. Because once you start exercising that hard, there's no blood flow to your digestive system because it's all going to your muscles, and then that food's not going to digest until we get oxygen. So redirecting blood flow is one of the things that means I shouldn't be eating a heavy meal before I exercise. If we look at the heart's relatively stable when we look at a percentage, all right? About 4 to 5% of my resting cardiac output works its way around to the cardiac arteries that are wrapped around the outside of the heart. When I'm exercising, it's still only 4 to 5%. But remember that it's now 4 to 5% of 25, not 4 to 5% of 5. So although it's the same percentage, it's a much larger volume of blood that is going to the heart when you're exercising. If you look at the brain, that's quite an interesting situation because the brain takes about 15% blood flow when you're at rest. The only energy substrate the brain can use is glucose, and it needs a lot of oxygen. Right? So 15% of your resting Q, about the same amount as is going to your muscles, goes to your brain. When we look at the percentage under exercise, initially it's like, well, how can I suddenly only get 3 to 4% of blood flow to my brain? But the brain is very, very, very intolerant of change. Right? It's a very delicate tissue, so it doesn't tolerate a decrease in blood flow. Then we see fainting. So anything more than a second or two, drop in blood flow to the brain, and someone is likely to be feeling faint, feeling woozy, if not completely passing out. By the same token, though, it can't tolerate a suddenly large increase in blood flow. So if I only drop to 10%, remember, this is the key. 15% of 5 liters, 3 to 4% of 25 liters. So actually, blood flow to the brain stays very, very similar. between rest and exercise. Because the brain tissue is so delicate, if I suddenly increase blood flow, it's going to increase the pressure in the brain, and there's nowhere for it to go, right? It's not like an artery that can expand. I have something in the way of the space expanding to allow all this extra blood flow. So the body has to adjust to make sure that not too much blood flow goes to the brain. So it stays very stable across exercise. Only a tiny, small increase when you exercise in blood flow to the brain. How do we achieve all this redistribution? So the arteries can vasodilate. I can increase the radius of the blood vessels, arteries and veins, and I can constrict, I can decrease the radius of blood vessels. So when we start to exercise, the central nervous system closes off the blood vessels to the stomach and the digestive system, and it widens the blood vessels going to the skeletal muscles. And then when part of that homeostasis, part of getting back to the resting state, is it will start to constrict the vessels it dilated and move the blood back towards the stomach so you can start digesting again. Okay, we're going to finish increasing venous return on Monday. And then we will also start chapter 7, which is looking at respiration.